Tokyo's story begins not with myth or prophecy, but with the hard certainty of geology. The city sits at one of the most volatile tectonic locations on Earth, where the Pacific Plate, the Philippine Sea Plate, and the Okhotsk Plate all converge in a complex triple junction. This region produces some of the strongest earthquakes recorded in human history, and Japan's scientists have spent decades studying the immense forces accumulating beneath the land and sea. Their findings are not comforting. Government panels warn that the likelihood of a massive magnitude 8 to magnitude 9 event along the Nankai Trough within the next 3 decades is extremely high, with probabilities that have steadily increased as new data emerges. The last major rupture in this system occurred during the 1940s, meaning another powerful event is already overdue according to the historical cycle. Tokyo has already lived through the consequences of a regional megathrust quake. On the first day of September in the year 1923, the Great Kanto earthquake struck with catastrophic force. Measuring an estimated magnitude 7.9, it devastated the region and triggered multiple firestorms that consumed large areas of the city. The disaster remains one of the deadliest earthquakes of the 20th century, and it reshaped Japan's approach to building safety and disaster planning. Yet even that tragedy represents only a fragment of what a full-scale Nankai Trough megathrust rupture could unleash on modern Japan. The danger today is magnified by scale. Greater Tokyo is now home to more than 14 million residents within its core wards, supported by one of the densest and most interconnected infrastructures on the planet. High-rise clusters, elevated expressways, deep subway networks, and intricate energy grids all rest on ground that constantly absorbs and stores tectonic stress. In recent decades, Japan has implemented some of the most rigorous seismic engineering standards in the world, incorporating lessons learned from past disasters, including the Tohoku Megathrust event of 2011. But even the strongest systems have limits when confronted with the largest possible earthquakes. In this simulation, the clock begins on an ordinary weekday. Commuters are on their way to work, classrooms are full, and the city hums with its usual energy. Deep beneath the ocean floor, southwest of Tokyo, along the Nankai Trough, centuries of built-up strain approach their breaking point. No one on the surface knows that a rupture line, 200 kilometers long, is about to give way, releasing a surge of energy powerful enough to affect the entire country. This is the beginning of a scenario shaped by real research, real history, and real seismic forecasts. It is not speculation born from fiction, but a grounded exploration of what could happen if the worst-case event struck without warning. Tokyo may be one of the most prepared cities in the world, but in the face of a true megathrust rupture, preparation may not be enough to preserve the city as we know it. The day a megathrust quake strikes begins not with a roar, but with a warning. Japan's earthquake early warning system, one of the most advanced in the world, detects the first seismic P waves traveling through the Earth's crust. Across Greater Tokyo, cell phones simultaneously emit loud alarms. Digital alerts interrupt television broadcasts, while loudspeakers in train stations and public areas broadcast a computerized voice. Earthquake detected, drop cover and hold on. Residents have only seconds to respond, enough to assume protective positions, but not enough to escape the city's built environment. At precisely 11:58 a.m., the first violent motions reach the surface. The initial P wave delivers a sudden vertical jolt, an almost imperceptible precursor to the impending chaos. Moments later, the S wave arrives, producing horizontal shearing, that shakes streets, office towers, and bridges with devastating intensity. In Shinjuku, skyscrapers designed with state-of-the-art seismic dampers sway dramatically, groaning under the stress, while ceiling panels, light fixtures, and unsecured furniture crash to the floor. Despite meticulous engineering, the magnitude of the quake, estimated at 8.7 to 9, pushes even the best construction beyond comfort limits. Below the surface, the subway system becomes a trap. Trains lurch violently, throwing passengers to the floors and causing overhead equipment to collapse. Emergency lighting flickers, then stabilizes, but the tunnels are blocked in several locations by falling debris. Millions of commuters, in the midst of peak hour travel, are stranded underground or amid streets filled with debris and moving hazards. On the streets, chaos dominates. The famed Shibuya Scramble Crossing becomes a scene of mass disarray as pedestrians are thrown off balance. Construction cranes, left unsecured at work sites, topple onto nearby buildings, causing secondary collapses. The roar of collapsing concrete and twisting metal fills the air. Sidewalks buckle, traffic lights crash, and vehicles are crushed or abandoned. In older neighborhoods of East Tokyo, wooden houses suffer catastrophic structural failure. Downed gas lines ignite fires in multiple locations simultaneously, while ruptured water mains hinder firefighting efforts. By 1 p.m., the first hour of the disaster has passed, leaving the city fragmented. Public parks and open squares fill with thousands of frightened residents seeking safety, but access roads are blocked by fallen debris. Hospitals, many running on emergency generators, struggle to accommodate the sudden influx of injured people. Rescue teams attempt to reach trapped individuals, but after shocks force repeated withdrawals. Communications remain compromised as cell towers and fiber optic networks suffer widespread damage. The city, once hyper-connected and organized, now functions as a network of isolated zones, each coping with its own emerging crises. By 4 p.m., fires begin to merge into larger conflagrations. Multiple firestorms spread across dense residential areas, with wind patterns intensifying their growth. Buildings not initially damaged by the shaking are threatened by embers and radiant heat. The skyline, normally a glittering array of lights, is now dominated by smoke and orange glows that pierce the approaching dusk. The first day of a Tokyo Megathrust quake has turned the city into a labyrinth of destruction, filled with trapped residents, collapsing infrastructure, and rapidly escalating secondary disasters. This is the moment when preparation meets reality. The city's residents have practiced drills, engineers have designed resilient buildings, and emergency systems are in place. But the scale of the event tests every limit. The first 24 hours set the tone for the survival of the city, the effectiveness of response measures, and the potential human toll. By mid-afternoon, the true scale of the disaster begins to reveal itself. Tokyo's infrastructure, though modern and highly engineered, faces stresses that no planning can fully mitigate. Roads are impassable, bridges sag or collapse entirely, and elevated highways buckle under the violent shaking. The city's subway and train networks, normally the arteries of urban life, are paralyzed, stranding millions underground and on the streets. Emergency vehicles navigate a maze of debris, slowing response times and isolating neighborhoods from rapid assistance. Fires erupt in dozens of districts simultaneously. Many stem from ruptured gas lines and electrical short circuits caused by toppled power lines. Dense wooden neighborhoods in eastern Tokyo, remnants of pre-modern construction, ignite within minutes. Gusts of wind carry embers into adjacent areas, creating the potential for firestorms. In some districts, multiple small fires merge, forming larger infernos that can burn at temperatures exceeding 900 degrees Celsius. Hot enough to weaken steel and ignite modern building materials, firefighters face blocked streets, collapsed water mains, and a shortage of available personnel, making containment almost impossible. Meanwhile, aftershocks, some registering magnitude 6 to 7, continue to rattle the city. Each tremor topples weakened structures, reignites fires, and causes panic among residents. Emergency shelters and parks and schools quickly become overcrowded, as tens of thousands seek safety in open spaces. Even these areas are not entirely secure. Falling debris from surrounding buildings presents ongoing hazards, and lack of sanitation and clean water begins to emerge as a secondary crisis. Critical services falter. Hospitals struggle to provide care as power intermittently fails, elevators stall, and operating rooms are forced to switch to battery-backed lighting. Communication networks are severely disrupted. Cell towers are damaged, telephone lines are severed, and internet access becomes unreliable. Coordination between city authorities, the national government, and the Japanese self-defense forces is slowed by this breakdown, making organized relief operations nearly impossible in the first hours. The economic impact starts immediately. Key industrial and commercial districts are damaged, halting manufacturing and logistics. Stock exchanges and major banks suspend operations. Transportation hubs, including Narita and Haneda airports, suffer structural damage and operational delays, isolating Tokyo from domestic and international support. Millions of commuters are trapped, and essential supply chains for food, fuel, and medical supplies begin to fray. By 8 p.m., as night falls, Tokyo is a city divided. Pockets of relative safety surrounded by zones of chaos, fire, and destruction. The fire's glow illuminates the smoke-filled skies, a haunting reminder of the quake's reach. Tens of thousands remain trapped in collapsed buildings, While the first estimates of casualties and property damage are staggering, though impossible to quantify accurately at this stage, the combination of structural collapse, fires, and overwhelmed emergency services sets the stage for a multi-day crisis that will challenge the city's resilience like never before. The first day demonstrates that even the most prepared megacity is vulnerable to the immense power of tectonic forces. While some areas endure relatively intact, the cascading failures across infrastructure, transportation, and utilities show how quickly a modern metropolis can fragment under the strain of a megathrust earthquake. Even amid chaos, Tokyo's advanced engineering and disaster planning begin to show their value. Modern skyscrapers, particularly in Shinjuku and Marunouchi, are equipped with tuned mass dampers, base isolation systems, and reinforced frames designed to sway safely during magnitude 8 to 9 tremors. These systems prevent catastrophic collapse for most high-rise buildings, buying crucial time for evacuation and reducing casualties. Bridges and highways built to absorb seismic motion flex rather than fail completely, although some older structures in less maintained districts sustain serious damage or partial collapse. The city's fire prevention measures also activate fire hydrants with backup reservoirs and automated sprinkler systems in modern complexes reduce the spread of fire in commercial areas. In districts with wooden housing, authorities prioritize open spaces such as stadiums, school grounds, and public parks as temporary fire breaks and assembly points. Despite these measures, high winds and ruptured gas lines allow some fires to continue spreading, demonstrating that no city plan can completely neutralize natural disasters of this magnitude. Underground infrastructure plays a critical role. The Metropolitan Outer Area Underground Discharge Channel, normally used for flood control, helps manage water flow from ruptured pipes and prevents localized flooding that could compound rescue challenges. Subway tunnels, though damaged, provide shelter for some who were trapped underground, and emergency lighting allows limited movement until power can be restored. The Japanese self-defense forces are mobilized quickly, coordinating with local police and fire departments. Helicopters survey the city from above, mapping damaged zones and identifying high-priority rescue sites. Drones and satellite imagery supplement these efforts, helping responders bypass blocked roads and debris-strewn streets. Command centers rely on hardened communications networks that survived the initial quake, allowing for a more organized deployment of resources than would otherwise be possible. Medical response is a race against time. Hospitals that remain operational triage patients based on severity, while mobile medical units and temporary field hospitals are set up in large parks and parking area. International aid is coordinated via Japan's diplomatic channels, although the scale of the disaster makes initial assistance limited. Early responders focus on rescuing individuals trapped in buildings, stabilizing severe injuries, and preventing secondary hazards such as fires, landslides, and water contamination. By the evening of the first day, the effectiveness of Tokyo's preparation is clear. Many modern structures remain standing, fires in commercial areas are partially contained, and emergency services are beginning to regain control in sections of the city. Yet the overall picture is sobering. Significant casualties, widespread homelessness, and crippling economic damage remain. The city's resilience is remarkable, but even the most advanced engineering and planning cannot prevent a megathrust earthquake from inflicting severe destruction in a single day. The hours following the quake highlight a critical lesson. Technology, planning, and human coordination can mitigate the worst effects, but survival in a city of 14 million during a mega disaster requires vigilance, preparation, and rapid action. Tokyo is far from destroyed, but the challenges ahead for recovery will be immense, spanning days, months, and even years. 24 hours after the hypothetical megaquake, Tokyo is unrecognizable. Streets are littered with debris, collapsed buildings, and damaged vehicles. Smoke and fires from ruptured gas lines still rise from the eastern districts, casting an orange haze across the skyline. Emergency shelters are overcrowded as hundreds of thousands of residents seek refuge, and makeshift medical tents work tirelessly to treat the injured. The human toll is staggering. In a worst-case scenario modeled for a magnitude 8 to 9 Nankai trough event, thousands could be killed instantly by building collapses, falling debris, and fires, while tens of thousands more sustain serious injuries. Evacuation routes remain partially blocked, slowing relief efforts and leaving some neighborhoods isolated. Communication networks are gradually restored, but for many, access to news, emergency services, and loved ones remains limited. Economic disruption is immediate and profound. Tokyo, the heart of Japan's economy, sees its financial markets, factories, and offices paralyzed. Power grids are partially offline, transportation networks are in chaos, and international trade faces delays as ports and airports sustain structural damage. Economic analysts estimate that a catastrophic quake along the Nankai Trough could result in losses reaching trillions of dollars across supply chains, infrastructure repair, and lost productivity. Environmental consequences also emerge. Collapsed buildings release dust, hazardous materials, and debris into waterways, while fires create air pollution and hazards for first responders. The combination of aftershocks and weakened structures poses ongoing risks, prompting evacuation orders from unsafe buildings. Experts warn that landslides and soil liquefaction in certain districts could continue for days, further complicating rescue operations. Despite the devastation, Tokyo's preparedness prevents total collapse. Emergency response protocols, trained personnel, and disaster-resistant structures save countless lives. Fire breaks, reinforced hospitals, and rapid deployment of the self-defense forces help contain further catastrophes, illustrating the importance of decades of seismic planning and lessons learned from past events, such as the 1923 Great Kanto earthquake and the 2011 Tohoku earthquake. Long-term recovery will be measured in years, rebuilding damaged neighborhoods, restoring transportation and utility networks, and providing mental health and social support to survivors are monumental tasks. Urban planners anticipate redesigning vulnerable areas with improved seismic resilience, while policymakers push for accelerated retrofitting of older buildings. International assistance may be required to supplement Japan's resources, as the scale of economic and infrastructural damage exceeds what even the most prepared cities can fully absorb. The day after the quake is a testament to both human vulnerability and resilience. Tokyo is not erased, but it is wounded. Its systems stressed, its people traumatized, and its economic engines slowed. Yet the survival of critical infrastructure and the rapid response demonstrate that with preparation, advanced engineering, and coordinated planning, even one of the largest and most densely populated cities on Earth can endure a catastrophic seismic event. The hypothetical scenario ultimately underscores a sobering truth. A megaquake could destroy the Tokyo we know in a single day, crippling its infrastructure, claiming lives, and causing immense economic and social upheaval. But the city's resilience, planning, and innovation provide a path for survival and eventual recovery, reminding the world that understanding and preparing for natural hazards is essential in the age of urban megacities. When people hear the word Megathrust, it might not sound like much, but in the world of natural disasters, it's one of the most dangerous things that can happen. A megathrust earthquake is not your typical ground-shaking event. These are the massive quakes that happen where two tectonic plates collide, with one being pushed under the other. These collisions happen in subduction zones, and when they release all that built-up pressure, the result can be truly devastating. To get an idea of what this could look like, we only need to go back to the year 2011, when Japan experienced one of the most powerful megathrust earthquakes ever recorded. That quake struck off the coast of Tohoku and caused not just intense ground shaking, but also a giant tsunami that swept inland, destroying entire towns and causing over $360 billion in damages. That single event remains one of the costliest natural disasters in history, and it shows just how dangerous these types of earthquakes really are. Now imagine if something like that were to happen again, but this time in a different part of the world that isn't as well prepared. Scientists have been warning about the Cascadia subduction zone along the Pacific Northwest coast of the United States. This fault runs from Northern California all the way up to British Columbia, and it has been quiet for a long time, maybe too long. Experts believe that if the Cascadia fault were to rupture in a full megathrust event, it could result in a quake larger than magnitude 9. That's strong enough to shake the ground for minutes, not just seconds, which is more than enough time to cause serious destruction. The first wave of damage would come from the shaking itself. Buildings not designed to handle that kind of movement would crumble. Bridges could collapse, roads would crack wide open, and power lines would snap. People in cities like Seattle, Portland, and Vancouver could be hit hard, and even areas far inland would feel the effects. Hospitals and emergency services would likely be overwhelmed right away, especially if communication systems go down too. But the shaking is just the beginning. One of the most dangerous parts of a megathrust earthquake is the tsunami that usually follows. Because the ocean floor gets violently shoved upward during the quake, it sends a massive surge of water racing across the sea. In some places, there would only be a few minutes of warning. Entire coastal communities could be swallowed by waves taller than houses. In low-lying towns near the coast, there would be little time to get to higher ground. What makes megathrust earthquakes so scary is that they don't just affect one city or one area. They can impact whole regions at once. Ports, airports, highways, and train systems could all be knocked out in a matter of minutes, and once that happens, getting supplies, rescue crews, or even basic help into the disaster zone becomes incredibly difficult. Even the ground itself could change forever. These earthquakes can cause the land to drop several feet, which means that some places that used to be above sea level could suddenly find themselves permanently underwater. That's not just a short-term problem, that's long-term flooding that could wipe towns right off the map. This is why scientists are so focused on megathrust earthquakes. They don't happen often, but when they do, the damage is off the charts. The next one could hit without warning, and if it does, the question is not just where or when, it's how bad will it be. One of the biggest challenges with megathrust earthquakes is how little warning people get before they strike. Unlike hurricanes or storms that can be tracked days in advance, these earthquakes happen deep beneath the surface, where pressure quietly builds over decades or even centuries. Then suddenly, everything gives way. That moment when all the energy is released at once is what makes these events so powerful and dangerous. Researchers are using tools like GPS satellites and deep sea sensors to try and understand where this stress is building and how close we might be to a major event. These tools can detect tiny movements in the Earth's crust, sometimes just a few millimeters a year, but over time those tiny shifts mean something big is coming. Some areas, like the Pacific Northwest, have been slowly moving for hundreds of years without a large quake to release that pressure. And when it finally does happen, it won't be a small release. It'll be the kind of sudden, violent shift that sends shock waves for hundreds of miles in every direction. The damage wouldn't just stop at buildings and roads. A megathrust earthquake would also severely impact basic infrastructure, especially utilities. Power grids would be knocked out, gas lines could rupture and catch fire, and water systems could break down entirely. That could leave millions of people without electricity, clean water, or heat. Especially if it happens during colder months. In coastal areas, seawalls and flood defenses might be destroyed by the tsunami, leaving communities vulnerable to more damage after the initial impact. And then there's the economic side. Ports that serve as hubs for imports and exports could be destroyed in minutes. In the United States alone, ports like Seattle and Portland handle billions of dollars worth of goods each year. If those are shut down, supply chains would be disrupted, not just locally, but globally. Everything from food and fuel to electronics and medicine could suddenly become hard to get. Large businesses might have backup plans, but small businesses and everyday people would struggle to bounce back. Insurance claims would flood in, and rebuilding would take years. Even 10 years after the quake in Japan in the year 2011, some coastal towns were still struggling to recover. Now imagine that kind of damage happening in several countries at once. That's the scale we're talking about when it comes to a megathrust earthquake. One of the most serious problems would be housing. With thousands or even hundreds of thousands of buildings damaged or destroyed, many people would be forced to leave their homes. Emergency shelters would fill quickly, and some people might not be able to return home for months or even years. In areas hit hardest by tsunamis, entire neighborhoods might be gone altogether. That kind of displacement can have long-lasting effects on families, schools, and entire communities. What makes all of this even more difficult is that megathrust earthquakes often strike areas that are heavily populated and near the ocean. That means there's a higher risk for loss of life, damage to property, and disruption to everyday life. These aren't isolated mountain regions with few people. They're often major cities, ports, and transportation centers that millions of people rely on every single day. And while scientists are getting better at understanding where these events are most likely to happen, predicting exactly when they will hit is still impossible. That's why so many researchers are focused on preparation rather than prediction, because when the next one hits, and it will be too late to prepare. One of the most dangerous things about a megathrust earthquake is what follows it. Massive aftershocks that can last for weeks or even months. Aftershocks might not be as strong as the initial quake, but they still cause serious damage, especially to already weakened buildings and roads, hospitals, emergency shelters, and communication systems that barely held together after the first quake could collapse entirely during one of these follow-up quakes. In addition to the shaking, the ground itself can shift in ways that completely change the landscape. In past megathrust earthquakes, entire coastlines have moved. In the year 2011, parts of Japan's shoreline shifted by more than 8 feet. That kind of sudden land movement can change the course of rivers, damage pipelines, and even affect underground aquifers. Bridges, railways, and highways could be left twisted or broken, cutting off entire regions from help. One of the most overlooked threats that follows a megathrust earthquake is disease. When clean water is hard to come by, sanitation systems are broken, and thousands of people are packed into emergency shelters, it creates the perfect conditions for illness to spread. In the aftermath of past earthquakes, outbreaks of stomach viruses, respiratory infections, and skin diseases have been common. If it happens in colder climates, things like hypothermia and frostbite also become major concerns, especially if heating systems are down for long periods. Farming regions near subduction zones would also be hit hard. Farmland could be flooded by tsunamis, contaminated with salt water, or completely shifted by the force of the quake. Crops could be wiped out for the season, and irrigation systems might be destroyed. That means fewer food supplies, higher prices, and even shortages, especially if supply lines are already down due to damage at ports and roads. There's also the mental toll. Survivors of megathrust earthquakes often deal with trauma, stress, and anxiety for years afterward. The constant fear of aftershocks, the uncertainty about whether homes and schools will ever be rebuilt, and the loss of loved ones all take a toll on people's health and well-being. Children in particular are deeply affected by the sudden change in routine and the chaos around them. Another long-term concern is how such a disaster would affect global cooperation. If multiple countries are hit at once, or if one country is hit so hard that it needs outside help, there could be competition for resources. Things like rescue crews, medical supplies, construction materials, and even food aid might not be available in large enough quantities to help everyone right away. This can lead to tension, especially if the disaster disrupts diplomatic or trade relationships. Scientists have even warned that megathrust earthquakes could trigger additional earthquakes in nearby regions. When one fault shifts, it can sometimes cause pressure to build up in surrounding faults. That means a single massive earthquake could start a chain reaction of seismic activity in places that weren't even directly hit at first. That kind of domino effect could cause problems across entire continents. Finally, there's the environmental cost. Landslides caused by the earthquake could bury forests, rivers could become blocked or redirected, and chemical spills from damaged factories or power plants could leak into the soil and air. In areas where nuclear power plants sit near fault lines or coastlines, there's also the fear of radiation leaks. These environmental disasters can take decades to clean up and may leave some areas unsafe to live in for generations. When we think about the next megathrust earthquake, one of the most important things to talk about is how communities can prepare before it happens. In places near subduction zones like the Pacific Northwest, emergency planners are focusing more and more on building codes. Stronger rules mean new buildings must be designed to sway with the ground rather than crack and fall. These changes might seem small, but they can save thousands of lives when a major earthquake hits. One major concern for coastal towns is evacuation. Because megathrust earthquakes often cause tsunamis, people near the ocean only have a short window, sometimes just 10 to 15 minutes, to get to high ground. That's why communities in places like Oregon, Washington, and parts of British Columbia have started building vertical evacuation towers. These structures are specially designed to withstand the shaking and the waves, giving people a place to run if there's no time to drive inland. In many areas, especially along the Ring of Fire, scientists are pushing for better early warning systems. These systems can detect the first signs of a quake and send out alerts before the worst shaking starts. In Japan, for example, their system can give people up to a minute of warning. That may not sound like much, but it's enough time to stop trains, shut down gas lines, and tell people to get to safety. The hope is that more countries will invest in these systems before the next disaster strikes. Schools and hospitals are also being reevaluated. Many older buildings weren't built with megathrust quakes in mind. In places like Chile and Indonesia, major hospital upgrades have started, so that emergency services don't collapse right when they're needed most. In the United States, California has already spent billions reinforcing hospitals to make sure they stay standing during a major quake. These upgrades are costly, but when disaster hits, they can be the difference between life and death for thousands. One challenge that's harder to fix is economic resilience. If a Megathrust earthquake destroys a major port, it can stall the economy of an entire country. Take the Port of Los Angeles or the Port of Vancouver, both handle huge amounts of cargo. If they go offline, it doesn't just affect the West Coast. It can delay supplies across the country. This is why disaster planning now includes alternative routes and backup transportation hubs to keep goods moving even if major ports are damaged. Another area being explored is how nature can help us. In some countries, engineers are working with natural defenses like coastal forests and wetlands to reduce the impact of tsunamis. These natural barriers can slow waves down and help protect inland areas. While they can't stop the damage completely, they can reduce it enough to save lives and property. People are also being taught what to do when the ground starts shaking. Emergency drills are now part of school routines in many earthquake-prone areas. Families are encouraged to have go bags ready, filled with water, food, first aid supplies, and important documents. Cities are running simulations that test how well their response plans actually work. The idea is to make sure that when the time comes, everyone knows what to do without having to stop and think. One of the biggest lessons from past megathrust earthquakes is that rebuilding takes time, years or even decades. Some areas in Japan are still recovering from the quake and tsunami that hit in the year 2011. It takes a long time to bring back roads, homes, businesses, and a sense of normal life. That's why planning for recovery is just as important as planning for the earthquake itself. Who will pay for the rebuilding? How can communities make sure they rebuild smarter and safer than before? And in the end, the next megathrust earthquake will not just test buildings and roads, it will test how well people can work together. From local leaders to national governments, from neighbors helping neighbors to scientists and engineers building better systems, every piece matters. There's no way to stop the next megathrust earthquake, but by preparing now, we can make sure we're ready to survive it and to recover afterward stronger than before. For millions of people living across the central United States, an ordinary weekday begins without any hint of the danger quietly locked beneath their feet. In cities like Memphis and St. Louis, the morning routines unfold just as they always do, unaware that deep below the surface, a long slumbering fault system carries stresses that have been accumulating for more than 2 centuries. This region, stretching across the Mississippi Valley, is home to one of the most surprising and least understood seismic threats in the country, the New Madrid seismic zone. Unlike the well-known faults of the American West, the New Madrid seismic zone sits in the interior of the North American plate. It traces back to an ancient rift system that never fully tore the continent apart. That incomplete rift left behind a weakened zone in the crust, creating the conditions for powerful intraplate earthquakes. Today, this network of faults runs through portions of Arkansas, Missouri, Tennessee, Kentucky, and Illinois, extending for roughly 150 miles beneath some of the most heavily traveled and densely populated parts of the Midwest and South. The historic record shows just how dangerous this hidden system can be. During the winter of 1811 and 1812, a sequence of major earthquakes shook the early American frontier. Modern geologists estimate their magnitudes to have been between the high 7 range and just under 8. Reports from that era describe furniture sliding across cabins, ground waves rolling through forests, and houses collapsing in settlements located hundreds of miles from the epicenter. The shaking was strong enough to ring church bells in cities on the East Coast and rattle structures far into what is now Canada. In the centuries since those historic events, the region has remained deceptively calm, but scientific measurements show that strain is again accumulating. According to long-term assessments by the United States Geological Survey, the probability of a strong earthquake of magnitude 6 or greater in this zone during the next 5 decades is between 1/4 and 2/5. The chance of a large-scale repeat of the early 19th century sequence, while lower, still ranges between roughly 7 and 10%. Numbers that seismologists consider significant for an area with aging infrastructure and limited earthquake preparedness. The danger is amplified by the geology of the Mississippi embayment. Thick layers of sediment fill the basin, and when seismic waves pass through these soft layers, the motion becomes stronger and longer lasting. This means that even a moderate earthquake here can cause unusually widespread damage, far more extensive than what the same magnitude might produce in regions with firmer rock closer to the surface. As we begin this scenario, the question is not simply whether the new Madrid seismic zone can produce another large earthquake. It can, and history proves it. The real question is, what would happen if such an event struck a modern and highly interconnected nation? With this foundation in mind, we now move to the moment the rupture begins. Our scenario begins in the early morning hours just after 2 o'clock. The region is quiet, wrapped in the stillness that settles over the central United States long before dawn. Beneath the surface, however, a critical threshold has been reached. Along the Real-Foot Fault, one of the primary structures within the new Madrid seismic zone, stress that has accumulated for generations finally overcomes the friction holding the fault in place. The rupture begins near the town of New Madrid in southeastern Missouri. The initial break releases energy equivalent to thousands of high-yield explosives detonating at once. Instruments would later estimate the earthquake's magnitude in the upper 7 range, comparable to the strongest events known from this fault system. In the first few seconds, a deep rumbling moves through the ground, too low in frequency for most sleeping residents to recognize. It seems to come from every direction, vibrating through homes, vehicles, and the soft sediment that fills the Mississippi Basin. Then the seismic waves arrive. Unlike the sharper jolts that are common along plate boundaries in the western United States, the shaking here is dominated by slow rolling motion. The Mississippi embayment is filled with thick layers of unconsolidated soil, and these layers amplify the waves dramatically. Entire neighborhoods are hit with swells of motion that lift and drop the ground in disorienting rhythms, making it difficult to stand, walk, or even crawl to safety. As the primary waves continue to propagate outward, the true damage begins. The saturated soils in many low-lying areas lose their cohesion, triggering widespread liquefaction. Streets buckle and tilt, and the foundations of structures shift as the earth briefly behaves more like a fluid than a solid. Sections of farmland slosh and slump as underground water is forced to the surface. In some places, plumes of sand and silt erupt upward, marking the violent pressure changes occurring below. The shaking lasts for more than half a minute, long enough to topple unreinforced walls, fracture underground utilities, and destroy older structures built before modern seismic standards were considered. In communities across parts of Missouri, Arkansas, Tennessee, Kentucky, and Illinois, an entire region is abruptly thrust into chaos, while most residents are still struggling to understand what is happening. As the final strong waves fade, an uneasy silence settles in. Power flickers across multiple states. Alarms blare, dogs bark, people wake to darkness, damaged buildings, and a sense that whatever has just happened is far from over. In reality, the first minute is only the beginning. In the minutes immediately following the rupture, the region enters a phase of rapid and compounding failure. The ground may have stopped shaking, but the consequences of those violent seconds begin unfolding at an overwhelming pace throughout cities and small towns located near the Mississippi River Basin. Older buildings constructed of unreinforced masonry suffer significant damage. Many of these structures were never designed with seismic forces in mind, and their brittle walls split apart under the stress. Entire rows of historic storefronts collapse outward into streets now littered with fallen brick, shattered glass, and sagging power lines. Transportation corridors critical to the central United States are struck especially hard. Highways that traverse soft sediment shift unevenly, creating sudden drop-offs, fractures, and buckled pavement. The soil beneath bridge supports has been weakened by liquefaction, and this instability places enormous stress on structures spanning major rivers. Several bridges across both the Mississippi and the Ohio experience severe deformation, with some losing sections as support columns tilt or sink into compromised ground. These failures instantly disrupt vital east-west and north-south routes, isolating communities on opposite sides of the region's waterways. And the electrical grid, which relies on a vast network of substations and transmission lines, faces cascading disruption. Many substations rest on soil that has now shifted or lost strength, causing transformers to crack or topple. High voltage lines snap under the combined strain of ground movement and structural damage to towers. As these failures spread across state lines, a large portion of the central United States is plunged into darkness. Some areas retain only brief pockets of power before automatic shutdown systems trigger to prevent further overloads. Beneath the surface, infrastructure fares no better. Water mains rupture as pipe joints are pulled apart by lateral spreading of the ground, leaving some communities without usable water and others experiencing uncontrolled flooding from broken mains. Natural gas lines, many buried decades ago without modern seismic reinforcement, break in multiple locations. In the minutes after the shaking stops, the smell of gas becomes noticeable in several neighborhoods, and small fires ignite where sparks meet leaking fuel. Communication systems falter just as urgently needed emergency responses begin. Cell towers that remain standing struggle to operate due to power loss and damaged fiber optic cables. Landline networks, so still an important part of rural communication, suffer breaks at numerous points. Residents attempting to call emergency services encounter busy signals or complete outages, leaving countless people without a way to report injuries, trapped individuals, or structural failures. Across multiple states, the combined impact becomes clear. Within less than 10 minutes, critical systems that millions depend on, transportation, electricity, water supply, gas distribution, and communication, are either severely compromised or entirely offline. And with no reliable means of contacting outside help, communities are left to confront the emerging crisis on their own as the full extent of the disaster begins to unfold. As the first hour passes, the scale of the disaster begins to become unmistakable. The central United States, a region not typically associated with earthquakes, is now grappling with conditions normally seen only in the most seismically active zones. The energy from the new Madrid rupture has traveled through the rigid continental crust with exceptional efficiency, causing strong shaking hundreds of miles from the epicenter. Cities such as Nashville, Little Rock, and Indianapolis experienced severe tremors, while residents in Chicago, Louisville, and Atlanta report buildings swaying in ways they have never felt before. Many are left stunned, questioning the reality of what they are experiencing. In the core zones, the destruction is both immediate and profound, with major roads blocked by debris and bridges compromised by subsidence and structural failures. Emergency responders are trapped, unable to reach the areas that need them most. Firefighters, police officers, and paramedics who attempt to mobilize face crumbled streets and fallen utility lines, often encountering the same hazards as civilians. Many stations themselves are damaged. Older firehouses and police facilities, built without modern seismic standards, are partially or completely destroyed, leaving first responders vulnerable and limiting their capacity to coordinate relief. Hospitals that remain standing face an influx of injured people while dealing with failing infrastructure. Backup generators provide temporary electricity, but without running water and with severed communication lines, triage and treatment are severely constrained. Medical staff struggle to navigate debris-strewn streets to reach patients, and those who do arrive find themselves working under extreme pressure, treating crush injuries, fractures, and severe trauma with limited resources. The first hour thus becomes a test of human endurance against overwhelming odds. Meanwhile, communities begin to experience secondary hazards. Flooding starts in low-lying areas, where water mains have burst and levees stressed by the shaking develop leaks. Liquefaction continues in areas of saturated soil, causing further collapse of streets and undermining standing structures. Sand blows erupt across farmland and urban areas alike, spewing sediment into streets, yards, and building foundations. Each of these hazards compounds the initial impact, further destabilizing buildings, roadways, and utilities. Communication, or the lack of it, intensifies the sense of isolation. Cellular networks are down over large areas, landlines are severed, and radio stations operate intermittently, if at all. Citizens have no reliable way to confirm the safety of family members or access instructions from emergency management agencies. In this hour, the combination of physical destruction and total communication blackout transforms what is normally a safe, quiet region into a zone of uncertainty, fear, and chaos. The human and logistical challenges that lie ahead are only beginning to take shape. As daylight breaks over the Mississippi Valley, the full scale of the disaster becomes visible. Entire neighborhoods are reduced to rubble, and the landscape itself bears the marks of the immense forces released during the earthquake. Large tracts of farmland are covered with sand blows, where liquefied soil and groundwater were expelled to the surface in miniature, volcano-like formations. Hillsides and river bluffs have collapsed in landslides, sweeping away roads, homes, and small communities. Even areas that survived the initial shaking now face new hazards as weakened slopes and fractured ground continue to shift. The Mississippi River, which has long defined the region's commerce and transportation, is now a source of catastrophe. Multiple levees were compromised or breached during the earthquake, allowing river water to inundate towns and agricultural fields. Floodwaters destroy bridges and further complicate efforts to move emergency personnel, food, or medical supplies. With major interstates impassable and rail lines twisted or submerged, the logistics of delivering aid become a daunting challenge. Airports in the region report cracked runways and damaged terminals, leaving air transport limited to a few isolated locations. The human toll is staggering. Hospitals overwhelmed by injuries face shortages of staff, supplies, and clean water. Thousands are trapped in collapsed buildings or isolated communities, with rescue operations slowed by both debris and the continued threat of aftershocks. FEMA and university projections suggest that a magnitude 7.7 event could displace over 730,000 people, forcing an unprecedented wave of internal migration and emergency shelter needs. Mental health crises emerge quickly as survivors confront trauma, loss of property, and the uncertainty of their future. Economic consequences ripple outward as well. The Mississippi River, blocked or rerouted in sections, halts barge traffic, carrying billions of dollars in goods. Local and regional businesses are destroyed or forced to close indefinitely. Repairing critical infrastructure, such as bridges, levees, and highways, will take years and cost hundreds of billions of dollars. Beyond the immediate financial impact, disrupted supply chains affect food, fuel, and manufactured goods nationwide, amplifying the disaster's reach far beyond the epicenter. In the weeks and months that follow, aftershocks continue to challenge recovery. Some exceed magnitude 6, damaging weakened structures and increasing the risk of additional collapse. Communities must rebuild almost from scratch, with engineers and emergency managers prioritizing the reconstruction of essential utilities, transportation corridors, and public safety facilities. Federal, state, and local agencies coordinate large-scale response efforts, but the scale of destruction in an area unaccustomed to major earthquakes makes progress slow and painstaking. The new Madrid seismic zone serves as a sobering reminder of the dangers posed by intraplate earthquakes. Unlike regions where seismic activity is frequent and public awareness is high, this central U.S. zone combines powerful potential energy with long intervals of quiet, producing a false sense of safety. The scenario is hypothetical, but based on scientific modeling, it demonstrates that the next rupture could challenge modern society in ways few have anticipated. The survival of communities, the resilience of infrastructure, and the capacity to respond effectively will define whether such an event becomes a tragedy of historic proportions or a testament to preparedness and adaptation.